Hi, Mr. Zapone here, bringing you another Student Terrorist production. Today we're going to be looking at projectile motion. What exactly is projectile motion? We have the fancy definition here. A projectile is any object given an initial velocity that follows a path determined by the gravitational and frictional forces acting on it. In simpler terms, gravity is, well, if you throw a ball. If you were to launch a ball into the air, the only forces that are going to be acting on that ball are gravitational and frictional forces. So projectile motion really deals with orbits, satellites in orbits. Whether you're kicking a football, throwing an object, shooting an arrow, if you want to hit a target from so far away, if you're hunting, if you want to throw an object with a maximum range, skydiver falling, etc. Projectile motion is, around us every day. It's important, and that's why we study it. And just to see an example of what we mean by projectile motion, here's a video of a cannon firing. That is a projectile. Once the cannonball is fired, the only forces acting on it are gravity and air resistance or friction. So that's our definition of a projectile. We see projectile motion in sports. This is the trajectory of a kicked football. Does anyone know what shape that is? When you have a projectile without air resistance, it does follow a parabola. The trajectory of it forms a parabola. In the real world, though, we know there's air resistance. So, if you stick your arm out of a window on the highway going 60 miles an hour, like wants to rip your arm off. The same thing happens when you kick a football or a ball in the air. It's got to travel through the air, and there's frictional drag. There's air resistance against the ball. And this video right here shows the difference between a projectile with and without air resistance. So here's the cannonball being fired without air resistance. And now we toggle the air resistance, turn it on, and we fire another one. And as we expect, it doesn't travel as far. Obviously, air resistance is going to slow you down. So you don't get quite as perfect parabola when you have air resistance. But most of the cases we look at, we're going to assume air resistance is negligible because it really makes the problems easier to solve for the level that we are currently at. We also know that if you have a projectile and you throw a ball, it's going to follow a curved path like you see in the picture. As the ball is moving forward horizontally, gravity is going to pull it towards the ground. And we also know that if you were to throw the ball faster, harder, it's going to go a little further. And if you were to throw it harder still, it's going to go even further than this. And that's kind of the trajectory of a horizontally thrown projectile. The cool thing about that is it really helps explain conceptually the idea of orbits. When an object's in orbit, we can think of it as falling forever, like the moon is always falling towards the Earth. And a good way to visualize this is with this little picture right here. So let's say you're standing on this tower and you throw a ball. You're a student, so you throw a ball. Obviously, you can't throw that far, so the ball just kind of plops right here. Let's say, someone else throws a ball. Let's say a guy named Wes decides he's going to throw a ball off the tower. And, he does a little better than you, but still not that good. He throws the ball and whoosh. And then someone else says, hey, wait a minute, I got this. So a guy named Chris decides, I can throw pretty far. So he gets on the tower and he throws the ball. And he does better than the rest, but it's still not quite that good yet. So along comes a guy named Michael. He decides to throw a ball off the top of the tower. And, he's a big guy, so he, got guns. He throws that ball really, really hard. And the ball kind of goes. It's falling, smashes into the earth like all the other ones. And then along comes, someone named Mr. Sapone. And, he really throws the ball really, really, really hard, just the right speed. He actually takes a little off because if you throw the ball too hard, it might actually leave the orbit of the Earth. But being the, guru that he is, Mr. Sapone throws the ball with just the right speed. Where it's going, it's falling towards the Earth, it's forever falling towards the Earth. So that's kind of the idea of an orbit. Forever falling. So just a little projectile motion, a little extension of it. We know that if you were to shoot a target really far away, I hope you know this, that if you were to aim directly at the target, as this arrow is, it's going directly at the target. If it's far away from it, you're going to miss the target. Why? Because when you shoot any projectile, it's over time, gravity is going to pull it down to a curved path. So you, in this case, you would actually have to aim above the target in order to hit the bullseye. This shows up, oddly enough, for those of us who are gamers in video games like Call of Duty and Battlefield. For any of you who played Call of Duty, you know that when you are sniping or if you're trying to shoot a target across a map, that there's no bullet drop at all. Wherever you aim is exactly where your bullet goes when you play a game like Call of Duty. The learning curve is very low on a game like that. Essentially, the coding of the game assumes that gravity is zero. Bullets do not drop over time as you shoot. Whereas if you were to play a game like Battlefield, if you played Battlefield, you know that when you're trying to hit a target that is far away from you, you actually have to aim slightly above the target because the game has more accurate shooting mechanics, and it assumes that your bullets are going to drop over time. So Battlefield gives you a more realistic shooting experience compared to Call of Duty. But just as an FYI, sometimes gravity is actually fabricated when you play Battlefield. If you look at the hacked gaming files, for some maps, the value of gravity is made to be, say, 15 meters per second squared. Why? Well, because even though bullet drop is considered a staple of Battlefield versus COD, some of the maps are too small to where bullet drop would be irrelevant for such a high-powered weapon when you're firing it. So in one case you have zero gravity, in another case you sometimes have a fictitious value of gravity. All in all, the shooting mechanics for Battlefield have more accurate physics than COD, but just a little FYI for that, for us gamers out there. Shooting mechanics. So now we're going to move on and we're going to try to answer a question. If we were to simultaneously drop an object and shoot an object horizontally from the same exact height, which one will hit the ground first? So imagine we have two, we'll say pool balls here, or cue balls, or just any objects that are round, circular. You have a compressed spring, and it's going to launch the blue ball that way, and simultaneously someone's going to drop the red ball. Which one hits the ground first? And an even stronger way to phrase this is to ask, if I have a bullet and a gun, and I shoot the bullet and shoot the gun and drop the bullet at the same exact time, which one hits the ground first? The fired bullet or the dropped bullet? And most people want to think, well, that fired bullet's going to go really, really, really far before it hits the ground, so that one should take longer to hit the ground. That is what most people will generally think, and that's not going to be true. We're going to see some examples of this, but a fired object and a dropped object will hit the ground at the same exact time. And I've tried to illustrate this here using shapes. So on the left we have the thrown ball, on the right we have the dropped one, and the curve's not perfect. I made this with PowerPoint shapes. But you can see that after at 0 seconds, these objects are at the same height, and you're going to throw this one and release this one. After 1 second, they're still at the same height. After 2 seconds, they're still at the same height. After 3 and 4 and so on. Whether an object is dropped or thrown, they are going to fall at the same exact rate, 10 meters per second squared, in accordance with gravity. So that's a kind of a cardinal point we're going through. These objects hit at the same time, and there's a little text here. It might be something worth writing down. The vertical component of motion has nothing to do with how fast an object falls. So this whole slide is going to be about the independence of horizontal and vertical motion, the independence of your x direction and your y direction when dealing with projectiles. Because gravity only acts in the y direction, up or down, so it doesn't affect anything in the horizontal direction. There's several ways to test this. I have this device right here. We'll see this in class. This is called a second law apparatus. It will simultaneously shoot a steel ball and drop one, and we'll see in class that they hit at the same time. You can try throwing a ball and releasing a ball at the same time. That's a little tricky. Or fire a Nerf gun and drop a dart, though you get a little air resistance there. And I have a couple activities in class we'll do with rulers and coins. You could actually demonstrate this very nicely, so we'll see that at the beginning of our next class. In the meantime, there's a video by Mythbusters where they tested this idea. Mythbusters actually went on a really long room, like a warehouse, and they know the muzzle velocity of a bullet when you fire it, so they know how far it's going to go. They calculate it, and you'll be able to do that soon. And they basically set a computer system up with the trigger, which basically, when the gun was fired, they simultaneously released a bullet where they expected the fired bullet to drop. And they had some high-speed cameras there, and they recorded it to see if, a fired bullet and a drop bullet do hit the ground at the same time. And of course, physics was vindicated or demonstrably true.
Which means rolling up the room 360
so this is about a 2-minute video. We'll just watch this.
Right about there. That's where they were landing out in the shooting range. So this is where I expect them to land here.
Okay. Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But
looks
from
pretty close.
360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves and a victory for physics.
So we see that 39.6 milliseconds, and that difference can be explained measurement error or simply air resistance. The bullet that's fired has to travel through a lot more air, so there's going to be overall a greater effect of air resistance on it. So it gets there 10 slower. They did say that time is smaller than the human eye can make out. A newer study by MIT suggests that 13 milliseconds as the limit. That shouldn't be meters per second. That should be milliseconds, and this should be milliseconds as well. So that is kind of debatable what they said there, but it is very, very hard at that time frame for you to really make out anything and make out any distinctions. You would actually see the bullets hit pretty much at the same exact time. You wouldn't be able to kind of figure out which one hit first. So physics wins as usual. So really the importance of this slide, the importance is really the independence of the X and Y components of motion. So we have some typically what would be considered notes here. You can copy these down, pause the screencast. We know that objects of different masses fall at the same rate. If you drop a bowling ball and a marble at the same time, they hit the ground at the same time. We've seen that earlier in the year. But now we know that no matter how fast an object is launched or thrown in the horizontal direction, it has no influence on how long it takes to fall. Vertical and horizontal speeds, vertical and horizontal components of motion, velocities, need to be treated separately. And if we do that, it kind of helps us solve problems like the picture poses below. If you know the muzzle velocity of a cannon, what angle do you want to, elevate the cannon on to sink the, invading pirate ship? So we'll be able to solve problems like this, and we'll start that in our next set of videos. But for now, we want to focus on what you see up here, the independence of the X and Y components of motion. So imagine here you're in a parking garage. You're in a car on top of a parking garage, and there's a science store down there below you, and they're having this big summer blow on Einstein dials. Buy one get one half, and you want to get there really, really, really fast before all the Einstein dials sell out, because who doesn't love Einstein dials? So instead of driving your car, down the ramp, 6 flights, going across the street, or instead of taking the elevator down 6 flights of stairs and then walking across the street to the science store, you decide to get there the quickest way possible. And that's Fast and Furious style. You decide to fly off one roof to the next roof. And so you're on top of the roof, you're holding the brake down, and you're revving up the engine, and you finally release. Now you drive your car off the edge of the building at a speed, an initial velocity in the x direction of 60 miles an hour. So your car starts flying off of the building at 60 miles an hour in this direction. Initially, your car has a vertical component of motion of 0 miles an hour. When you drop an object, when you have an object in free fall, when it first releases, what's its initial velocity? Going up and down. Well, it starts at 0. And that's a free fall problem. So initially the car has a velocity going down of 0 miles an hour right there, and it has a horizontal component of 60 miles an hour. And as you continue, we know it's going to take a curved trajectory. It's going to kind of go down in a curved path. And as you do that, as you keep going forward, notice the velocity of the vehicle in the x direction. It's still 60 miles an hour. This velocity is not going to change. The only force acting on this, assuming air resistance is negligible, is the gravitational force. The gravitational force only works up-down. It only works in the vertical component. So it has no influence whatsoever over the horizontal speed of this vehicle. So this horizontal speed is going to remain constant throughout, because unless there's an outside force acting on it, well, this object in motion is going to just stay in motion. It's going to maintain the speed it has until something slows it down. But what gravity is doing is gravity is pulling this object down. And in fact, your velocity in the y is increasing. So this vector would actually be a little bit bigger. As you drop an object, it falls from rest, but it speeds up as it's going down. So if we were to draw the next step in this diagram, velocity in the y would still be increasing even more. And velocity in the y would be increasing, but velocity in the x would not be increasing. The horizontal component of your motion is not changing. Gravity does not influence that. We have to treat the motion in the horizontal direction and the vertical direction separately. So in your rush and your zeal to get your Einstein dial, of course, you get to the store very fast. But like Paul Walker said in the movie, cars don't actually fly, so you will die. In this case, you're not going to be able to drive a car out of a window from one building into another like they did in the movie. But the important part for you to see here is the independence of the two directions of motion. When you have velocity in the x, it's completely distinct, completely independent of your motion in the y. And gravity only changes your velocity in the y direction. So basically, you treat the motion separately, and this is kind of a free fall problem, and it's just a motion in the horizontal direction. So just the most important part is, please realize and get it through your head, the whole point of this slide, there is an independence of your horizontal and vertical components of motion. We treat them separately. So that's the basics of that. Just as an FYI, or just as a quick question, at what point in the path of this car is its acceleration the greatest? If I ask you a question like that on the test, at what point is the acceleration the greatest? And I'm hoping you realize that we know the our horizontal velocity is the same throughout. That's not changing. The velocity is increasing as you're going down, getting the fastest just before impact. But acceleration, well, in this case, acceleration is just 10 meters per second squared. So acceleration is actually constant throughout. The acceleration does not change. That's sort of a trick question. And just to drive this point home, we're going to look at one more case. This case, we're kicking a football off a tee. And we want to realize that gravity does not impact your horizontal motion. When you kick the ball at this angle, This is going to kind of be like a vector. Like you're kicking the ball, say 20 meters per second at 45 degrees. Well, you can break this vector. If this was a vector, you're going to break it into a vertical component, or a horizontal component, I should say, and a vertical one. And we'll do that in the next slide, but realize that the horizontal speed of this ball is never going to change. It's going to stay the same until it hits the ground. What does change is the velocity in the y direction, because the only force acting on this, assuming air resistance is negligible, is gravity. We know that when we throw a ball up in the air, we learned that in the last unit, if you throw a ball up at 5 meters per second, it's going to go up, gravity is going to be slowing it down, it's going to stop, velocity is 0 at the top at its highest point, then it's going to start increasing its velocity as it comes down. And it's going to hit your hand at the exact same speed you released it with. And the same thing is true for this football. You're kicking the ball. Initially, it's going up. It has an upward component, very rapid, very fast, high velocity. Now it's slowing down, denoted by a smaller arrow. So finally, your velocity in the y direction is 0 at the apex, at the top of the ball's trajectory. Now finally, the ball is going to start going down, speeding up. This velocity is equal and opposite, right? If this was 5 meters per second up, this is 5 meters per second down. Same thing here. If this was 10 meters per second up, this is now going to be 10 meters per second down. So the idea here is that the vertical and horizontal components of motion are independent of one another. Gravity only acts in the y direction. It has no influence over the x direction. And just to kind of make sure we understand that, we're going to look at 3 ranking tasks. These ranking tasks are on your homework. I encourage you to pause the video and to try them yourself. It should only take a few minutes. And then before you get the answers from me, I think that would help the learning process a little bit better. So let's take a look at this to make sure we actually understood the content of this screencast. We have a horizontally launched toy trucks. So you have a toy truck is launched horizontally from a table of height h. In case A, the toy truck leaves the table with a speed of v. And in case B, the toy truck leaves the table with a speed of 2v. So you have 2 toy trucks leaving a table at the same height. One is traveling twice as fast as the other one. And we have a student comparing the time the trucks are in the air states, the faster you go, the less time it takes to get there. The truck in case A will be in the air longer. So what, if anything, is wrong with this statement? If something is wrong, identify it and explain how to correct it. If the statement is correct, explain why. So this is one of our typical ranking type tasks. So please pause the video before I give you the answer. So hopefully the entire kind of point of this slideshow was that an object dropped and fired will hit at the same time. It doesn't matter how fast you fire the object. So I'm hoping you realize that despite the fact that this truck is going twice as fast, it's not going to hit the ground any sooner. Both trucks are going to be in the air at the same amount of time. Case A, the student is incorrect. The truck will not be in the air longer. The only thing that will happen is if this truck is going twice as fast, they're going to take the same amount of time to hit the ground. This truck B, will travel twice as far in the vertical direction, but it will not hit the ground any sooner. So if you're looking for a kind of a written answer to that for your homework question, to make sure you receive full credit on that one, there it is. You can pause this and copy that down. We know the objects hit the ground at the same time. The horizontal velocity is independent of the vertical velocity. We have to treat them separate. They hit the ground at the same exact time. Case 2, and again I encourage you to pause this and kind of do this yourself before I give you the answer. All of the cannons in the figures are identical. So we have 4 cannons, and they're all aimed at the same angle of 35 degrees to the horizontal. The cannonballs are all the same size and shape, but the masses of the cannonballs, as well as their speeds as they leave the cannons, are different. Rank the acceleration of the cannonballs when they reach their highest point. So we know when we shoot these cannons, they're going to follow sort of a curve path, right? A parabola, negating air resistance. They want to know the acceleration at the highest point. And be careful with this question. They're not asking for velocity. What's the velocity at the highest point in the up-down direction? You throw a ball up in the air, it slows down to 0. So your velocity at that point would be 0. So you start speeding up. But what is the acceleration of any object dropped or thrown on the surface of the Earth? 10 meters per second squared. This is a trick question. All of these objects, all of these cannonballs, regardless of their mass, regardless of their initial speed, throughout their entire range of motion, they will always be accelerating at 10 meters per second squared in the downward direction towards the surface of the Earth. So this was a trick question. The acceleration is all the same. You would actually check this box right there. And again, there's a little write-up of that if you need a visual of that for your homework. It's all the same. All are influenced by gravity, fall at the same rate, 10 meters per second squared. Even when you have a velocity of 0 at the top, you're still accelerating downwards at the same speed. And last one, unfortunately, I gave you the answer already to this. I forgot to use the PowerPoint animations to click it in. All of the arrows shown were shot from the same height and at the same angle. Though the arrows have the same size and shape, they are made of different materials, so they have different masses, and they have different speeds as they leave the bows. Rank the maximum height the arrows reach. So we have 4 arrows. This one's 90 grams, firing at 10 meters per second, 180 grams at 12 meters per second, 100 grams at 16, and 180 at 10. So these two cases, A and D, have the same speed. But this arrow is twice as heavy. Which one will go higher? And that's a tricky question. What we need to realize here is that mass doesn't matter. Remember that a bowling ball and a marble fall to the ground at the same time. So they're giving you extra information here, not to trick you, but making sure you realize not to use it. So the mass doesn't matter in these cases. We know that heavy and light objects fall at the same exact rate. So this mass is really unnecessary. So now if you think about this problem, it becomes very easy. If you were to throw a ball up in the air at 16 meters per second and someone would only throw a ball up in the air at 10 meters per second, whose ball would go higher? Obviously the ball that is thrown harder and faster. So if we were to rank these, this ball is being thrown the fastest, so C is going to be faster than B, which is going to be faster than D and A, which are equal. These two, A and D, should go the same exact height. So you would put CB, and then D equals A. And that's how you do that, and the reasoning is explained below. So that hopefully we have an understanding of the independence of the horizontal and vertical components of motion. And you do have a homework assignment tonight. Complete question 24 on your homework. It should only take you 5 or 10 minutes, probably 5. Just get an answer to these, and we'll collaborate in groups in the beginning of class after we do an activity, and we'll then go over them to make sure we really understand projectile motion in a qualitative capacity. If you can answer these questions correctly, then you fully got it. This is Mr. Spohn. I'm out.